Hello everyone, thank you so much for joining us today. I hope everyone's doing well and staying safe out there. My name is Victoria and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all today to our webinar entitled Fatigue and Drilling Operations. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Phil Ward. Phil is a principal engineer at 2H. He has over 11 years of engineering experience in structural dynamics and fatigue analysis. He's been working in the oil and gas industry since 2009, including design and numerical analysis of riser systems, drilling engineering analysis, structural monitoring, and well casing design. He's currently working for 2H Offshore in Houston, having previously been based in Aberdeen for the majority of his career. Phil holds a master's degree in engineering from Cambridge University, is a chartered engineer, and a member of the Institute of Mechanical Engineers. So with that, I'll pass things over to Phil to get us started.
Thank you, Victoria, for the warm introduction. I'm very excited to be here today speaking on this topic and hope you'll all find the information useful. As Victoria said, my name's Phil and I've been with 2H for about 10 years now. Although I'm currently based in Houston, most of my career was spent in Aberdeen, and during that time I was involved in hundreds of analyses of subsea wells, most of which included some form of fatigue analysis. And as we were out and about presenting results to clients, many questions used to come up and we used to get very similar questions from different people. So what I've tried to do with this presentation is to pick some of those questions and answer them in a logical manner. So I picked 5 in particular. First of all, what is fatigue? What is it that we're actually dealing with and why does it apply to subsea wells? Nextly, what does a fatigue life result really mean? So after you've done the analysis and you get a result out, often it's expressed in terms of days or years, there's a number associated with it. But what happens at that point in time? What does that result actually correlate to? The next question is, how can I avoid fatigue concerns in my project? So what are the decisions that are available to you in design and what effects do those decisions have in terms of your overall fatigue life result at the end of the process? And that's going to focus mostly on new drill wells where you can affect the design, but there's also a question about the older wells that already exist that you might want to go and intervene on, go and work over, go and abandon. What can you do if those wells don't have sufficient fatigue capacity left? And then finally, a question that we often get is, how good are your models? So how close to reality does your analysis actually get? So starting off then, what is fatigue? And probably the classic example of this is an experiment that you might have done with your kids during lockdown, or one that you did back at school, where you take a paper clip and you bend it backwards and forwards until it snaps. And what you're doing there to that paper clip is you're exposing it to cyclic loading. Now, you tend to be bending it quite significantly in the paperclip example, but you don't have to get a fatigue issue. And often for subsea wellheads, we're operating entirely within the elastic regime. But there's really 3 different phases to fatigue. The first of all, the initiation phase, which is where you bend it enough at a certain threshold to initiate a crack somewhere on the surface of the material. Then, as you continue to load it, you propagate that crack through the thickness until it reaches a threshold size where the stress intensity at the crack tip is sufficient to overcome the toughness of the material, and you end up with a fast fracture, a brittle failure. And you see that on the picture to the left-hand side here, where you've got the initiation site down at the bottom of the sample, the smooth surface associated with the propagation of the crack to that threshold, and then the rough surface associated with the fast fracture and the brittle failure. But fatigue life really is the combined duration of the material and the loading in all of those phases. And for any structure, it's a function of the structure's geometry, its material, the fabrication techniques used to make it, and the loading that it is subjected to, and we'll pick up on each of these themes as we go through the presentation. In the subsea wellhead world, there are really 2 fatigue mechanisms that we worry about, environmentally driven. The first one is current-driven fatigue, which is this vortex-induced vibration, or VIV fatigue, and the other one is wave-induced fatigue that I'll talk about on the next slide. For VIV, when you place a cylindrical body into a current flow, you'll tend to get vortices shed on the leeward side of that pipe, And you sort of see that in the diagram up towards the top left of the slide. Those vortices tend to be shed from one side of the pipe and then the other in an alternating manner. That creates a pressure wave that moves the pipe backwards and forwards and then causes your cyclic stresses and your fatigue loading. Now that's not too much of a problem typically until the frequency with which those vortices are being shed lines up with the natural frequency of the riser pipe, and then you get resonance occurring. That's when your motions become amplified and so do your damage rates. So typically for VIV, we tend to be more worried about it where we have faster currents, and it seems obvious. About a 1 meter per second 2 knot threshold is key for that. Smaller diameter risers that are easier to excite, and also for deeper wells. So increasing water depth, greater than about 300 meters or so is the threshold. And the deeper water is more of a problem because we have a greater length of riser that's exposed to the current. We have more region over which power can be driven into the system through this excitation effect. But also we get high damage where in the wellhead, where the riser frequency tends to line up with the BOP frequency. Because if that resonant effect then goes on to excite the subsea equipment, whatever's sitting on top of the wellhead, then you'll get a significant damage in your wellhead equipment. But the key takeaway is that VIV is an on-off effect. If you break that resonance behavior, then your fatigue damage rates will drop way off. That's not true with wave fatigue, which is constantly being accumulated at some rate or other. You've got the wave action on the vessel, on the sea surface, moving that around, and some of those motions get transferred down through the riser. But then you've also got the direct action of the wave on the riser itself as well, through drag loading. So the opposite of VIV here is that we're more concerned about wave fatigue in shallow water depth, so below that kind of 300 meter threshold. And the reason for that is that the wave is occurring at the top of the system, and the longer you make your riser, the smaller the percentage of it that's being excited by the wave, and the more the percentage of it that's helping to damp out those motions before they get transferred down to the wellhead. We're also more worried about wave fatigue for the most commonly occurring waves. That kind of makes sense. But also those waves are around about the 5 to 7 peak period second regime, which is where we start to get into that resonance behavior in these kind of water depths as well. Again, both resonance of the riser, but also the BOP and the subsea equipment. And as I said, constantly being accumulated. Your wave height will rise and fall, as will your damage rate, but you'll always be accumulating something. But for both mechanisms, the technique that we use to assess them is pretty similar, and we call it the SN fatigue assessment, where S is stress and N is number of cycles. And I've laid out 7 different steps to that process on this slide, but really the first 2 are done for us, and we take those from the design codes. This is where people have tested samples of different materials, different fabrication techniques, different welds, etc. They've tested them at different stress levels and seen how many cycles of those stresses it would take to fail the sample, and that gives us our S stress N number of cycles relationship. So for any given project, we usually start at step 3, which is generating our stress time traces for the loads we expect in our system during the service life, and that's the global analysis step. After we have those stress time traces, then we have to do something with them, and that's the remainder of the steps, which is what we call post-processing, which is quantifying the number of stress cycles of different magnitude that exist in that time trace, and then comparing those number of cycles to the number of allowable cycles that we extract from the SN curve. Finally, we add up all those ratios to get our damage, and then the last step, step 7, is applying a safety factor to account for the variability. And that's where we tend to start losing people in terms of the conservatism that's inherent in the assessment. I'll go through that in some detail in a bit. But the approach itself has been around a very long time now. It's well recognized in the industry, and it takes different pieces from each of these design codes that I've put down here and some others. And again, these will pop up as we go through the rest of the presentation. So, as I said, we start on any given project with step 3, which is global modeling. We call it global modeling because we're doing exactly that. We're modeling the whole system in one go. So we typically start at a point that's about 50 meters or so below the mudline. That's deep enough for all the forces and bending moments and everything exciting to have dissipated in the soil above that point. Then we model the conductor up to the wellhead. We have the subsea equipment, the BOP stack, the LMRP, etc. Go up through the riser joints, telescopic joint, up to the drill floor of the vessel, whatever's attached to our well. That allows us to have all of the behavior connected together in one model, and we can expose the whole system to the environmental loads. So we get the action of the wave on the vessel, as well as the direct action of the wave on the riser, for instance, all captured in one model, and we can extract the structural response of each individual component in that system, again from a single model. That approach is well recognized. It's outlined in DNVGL RPE 104, for instance. Soil modeling will take information from API 2A, 2Geo, and other papers associated with different soil types. And there are plenty of industry-recognized software packages that are essentially purpose-built for modeling long, slender systems, such as this. I put a couple of examples here on this slide, but there are others available too. So once we've built our model, one of the key things is then to make sure that we're exposing it to appropriate environmental loads. For wave fatigue, those loads tend to come at us in these diagrams, which are sea-state scatter diagrams. And we've got bins on this diagram with peak period bins along the top, and we've got significant wave height bins down the side. And the colours show us where we expect most of our wave occurrences to happen. And the red is the most commonly occurring bins. So that's between those 5 and 7 second peak periods that I talked about before that are likely to link into different resonant frequencies in your system. Well, it's said to use appropriate information, and that's important. And by that I mean site-specific, so it belongs to the location where you're actually going to be performing the operations, but also appropriate in terms of the time of year and the season that you're going to be doing those operations in. So if you're going to be doing them in the summer, then you want to take the benefit of having summer weather, so the diagram should represent that. For VIV, it's a similar story. You need to make sure that you're using appropriate current profiles. Usually in the MetOcean data, you'll start with extreme return period current profiles, which are shown on the left-hand side here. And you've got a red line, a blue line, and the green line with current speed along the top, and then water depth down the side. And these are the values or the profiles that you'd expect to occur once in each of these given time periods. So the red line once in 1 year, blue line once in 10 years, etc. That's fine, but these will be quite damaging currents, so you get a lot of fatigue damage from these, but also they don't occur that often, right? So we need to make sure that we're assessing everyday currents as part of our fatigue assessment. So we'll combine those extreme profiles and we'll convert them into exceedance currents, such as shown on the right-hand side. These are lower current speed values that will occur more often. We'll run each through the model, calculate the fatigue damage rate under each, and then multiply those by the percentage exceedances to get our overall fatigue number. But again, they should be site-specific, and they should be appropriate for the seasons that you're doing the operation in. So once we've built the model, we've loaded it with the environmental conditions, we've agreed they're appropriate. Now we need to convert the outputs into our stress cycles. And there's different steps to that. The first one is to extract time traces of bending moment and tension at each node of interest. So we can extract them from any point of the system because we're using this global modeling approach. We then convert those outputs to stress time traces, considering the geometry of each individual component and beam theory, and also the appropriate stress concentration factors for each component. And by that, I mean the ratio between the peak stress at a location that might be more heavily stressed than average, and the average stress across the wall thickness. So this applies for things like connectors, where you might have a peak stress in a thread, for example, relative to the average stress across the main part of the wall. Once we have our stress time trace, we then cycle count that time trace using fairly standard techniques like rainflow counting as one example, and the output of that is a histogram. That histogram, such as the example here, tells us how many cycles we expect to see over a given time period at what stress range. And there's two different colors of columns on this plot. I've got red columns for operations drilling without the subsea tree in place, and I've got blue columns for operations drilling with the subsea tree in place. And you can see that the blue diagram is more onerous, it goes to higher stresses and it has more cycles in it. That kind of makes sense because we're increasing the size of the stack sitting on the wellhead. And what this diagram tells us is most of the information that we need to do our damage assessment. And the damage assessment formula is the one that's shown in the box in the middle of the slide. So first of all, I and K. So K is the total number of columns that we have, the number of bins in our histogram. So we know how many of those we've got. And then for each of those, for each I between 1 and K, we can extract from this diagram the number of cycles that we expect, which is little n. So the only thing missing from this equation that we can't tell from this diagram is big N, and that information comes from the SN curve. The SN curves, I said that they come from design codes, but it's worth spending a moment or two just examining how they're actually formed. And the way that they are formed is that you take the sample of the material that you're interested in, whether it be a base metal or a welded detail, or whatever it is, and you expose that sample to a bending moment or a known stress range. And you bend it backwards and forwards, just like the paperclip that I started with, until that sample breaks. And you count the number of cycles that it took to break that sample, and you mark it on your plot. Do that again with a second sample and a third, until you've got enough information to understand the distribution of failure at that particular stress cycle. Then you increase the stress on the component, take another sample, repeat the test and get a value of n, another sample, and again until you've got enough information to build up that distribution. And you keep doing that at enough different stress levels until you've got sufficient information to draw a best fit mean curve across the entire SN domain. And then the final step to convert that to a design tool is to pick a design curve which is usually placed 2 standard deviations below the mean, or around about a failure probability rate of 2.3%, 23 samples-ish in 1,000 samples that you've been testing. One of the key things about SN curves is that because you're taking the samples through to failure, they account for both initiation and propagation phases of fatigue life. You'll have different ratios of those phases for different types of sample, but you're encapsulating everything in one curve. So we have our design curve, which is 2 standard deviations below the mean. From our histogram, we extract for each stress range level, S, the number of cycles that we expect, little n, and we also calculate from the SN curve the number of allowable cycles at that same stress range, which is our big N. Then we take each of those little n over big N ratios and add them all up to calculate our fatigue damage. And for subsea structures, the SN curves are available in DNVGL RPC 203, and that's usually our primary reference for this information. Then the final step in this process, step 7, is the application of that safety factor. And really there are 3 main reasons for doing this. First of all, to account for variability in the loading. So certainly for predictive analysis, where you're planning a forward-looking operation, you have to use an assumption about your environmental data. You have to use an average, essentially. Now, you might narrow that average down to be summer weather or winter weather, whatever it is, but the actual summer that you go out there to do it might be a more benign or a more onerous summer than the average conditions. So there's going to be some variability there. There's also some uncertainties in the design data. Perhaps your real-life conductor stick-up is slightly different from your plan and design, for example. So you need to account for that as well. But probably the most important one of these 3 different aspects is to apply a safety factor to ensure the probability of failure associated with the fatigue life result is appropriate for the activity. And because we're dealing with drilling hydrocarbon wells here, where we've got an environmental risk, we've got a human risk, and everything else associated with that, normally those activities are classed as high safety class in DNVGL's STF201 world, and the acceptable failure probability associated with that safety class is somewhere of the order of 10 to the minus 5. And they say that if you apply a factor of safety of 10, then you should be operating somewhere down at that level in terms of failure probabilities. If you have a lower safety class operation, then you can accept a higher failure probability, up to 10 to the minus 3, for example, and then you can apply a lower factor of safety, like a 3. Now in API's world, they have a slightly different logic, but they end up in a similar place. What they do is they say that if you can and you are actually going to inspect your components during the service life, then you can use the fatigue factor of safety of 3. But if you can't or you won't inspect during the service life, then you must use the 10. So the numbers are the same, but the logic is slightly different. So we do all that and we get a fatigue life result out. But what does that fatigue life result actually mean? So on this plot, I've got increasing life along the x-axis, and I've got probability of failure at that life up the y. And the first thing that we can mark on here is a known variable, which is our service life. That's the time that the drilling riser will actually be connected to the wellhead. Now, we're then going to pick an appropriate factor of safety. Let's say it's that 10. And we're going to multiply our service life by that factor of safety to get our design life. And the design life is essentially the target for our fatigue analysis. So before we apply a safety factor, what raw number do we need to get out of the fatigue assessment to actually meet our fatigue requirement? And that's the design life number here. So let's assume that we do that and we get a fatigue result from the analysis that's exactly equal to our design life. What that really means is that at that point in time, we've got around about a 2.3% chance of failure. Now, there's a massive assumption that goes into this, which is that the loading and the analysis is a perfect representation of reality, and that 2.3% just links back to the selection of the design curve from the SN world, from the SN testing, and the fact that we're 2 standard deviations below the mean. As I said before, there's a lot of variability around this result, so really that point just represents one point on a big distribution. And by introducing that safety factor, what we're then doing is we're controlling the amount of that curve that's below, or a time period that's shorter than our service life. And the area under that curve to the left of the service life is the probability of fatigue failure within the service life. So if we've picked our factor of safety correctly and we've met our design fatigue life target, then that is an acceptable area. If you pick a lower factor of safety, for example, what you're essentially doing is accepting a shift of that curve to the left and a greater probability of fatigue failure within the service life. So the fatigue life then is the time with the drilling riser connected before the allowable probability of a fatigue failure is exceeded, and that's kind of the definition that I use. Alright, so that's focused mostly on analysis so far. Let's shift gears a little bit and look at design and avoiding fatigue issues. For new drill wells, fatigue issues can generally be designed out of the project. That might be through picking equipment of a sensible size or suitable size, like your conductor sizing or your surface casing sizing, or it might be picking fatigue-resistant equipment, like certain connector types or wellheads, or it might be placing that equipment in a place where it's not going to be exposed to peak loading, and therefore it's going to be exposed to reduced fatigue damage rates. The final thing that you can do here is you can pick a vessel with favorable dynamics, so one that's not going to exacerbate any resonant effect, is going to have its peak motions in a peak period that's outside the main wave occurrences, for example. Now, for intervention operations on older wells, you can pick a vessel again, but apart from that, there's not really a lot you can do with the design because the well's already in the ground. So here, this is probably where you're going to need to look at refined analytical approaches. It may be where you need to look at risk assessing reduced safety factors, particularly for abandonment operations or late life operations. Or you may need to look at other mitigation strategies such as structural monitoring or structural reinforcement. And we've got some slides on those towards the end. The typical points of concern within a subsea wellhead system are the ones that are identified on this slide. So we have a fatigue life plot on the left. So we've got elevation for mudline on the y-axis, and we've got fatigue life in years along the x-axis. And you see that the main shape of both curves, one's for the conductor and one's for the surface casing, the main shape is dominated by a curve that peaks around about 4 meters below the mudline. And that's dominated by the bending moment distribution in the upper section of the soil column. But then we step out from that main curve at different details. So we look at the surface casing connector that's down around about -9 and a bit meters, and we have the conductor connector that's a bit lower at -11 meters or so. They have big spikes that step to the left of the main curve, and we've got a similar story at the well below the low pressure housing and the well below the high pressure housing, and also the connection at the top of the high pressure housing as well. And those spikes are caused by something interesting in the fatigue world, so that might be either a geometric feature, such as the thread or a gouge or a notch or something associated with the connector that gives us a high SCF because we have a stress razor, or it might be a weld that through the manufacturing process has a higher probability that there's a flaw already existing within that section of the material as opposed to the base metal. The first one increases our stresses through the SCF. The second one, the defect in the weld, reduces the amount of cycles that we can have because we've already got a defect of a certain size in the material. So that reduces the SN performance. And some of the things that you can do in design to improve your fatigue resistance, we'll go through in the next few slides. This first one is looking at conductor size. So for this particular example, it's a certain configuration in a certain location, so there is some variability. We're comparing the fatigue response at 2 different welds in the system across 4 different load cases for different conductor sizes. And we start with a 30-inch by 1.5 inch wall thickness conductor to the left, load case 1. We go up to 36-inch by 1.5 inch load case 2, and then continue to increase wall thickness and then OD as we go to load cases 3 and 4. And you'll see that increasing from 30-inch to 36-inch gives us about a 5 times improvement in our fatigue result. And we keep on improving as we go bigger, although those improvements tend to level off. So that increase from 30 to 36 is the key one here, and that's one that many people use in the design of fatigue critical wells. Conductor stick-up is another one. I kind of mentioned this a bit earlier on, but you can imagine that as you increase your conductor stick-up, so you increase the height of your wellhead above the point where it's being supported by the soil, you're essentially increasing the lever arm effect from your BOP and your LMRP stack sitting on your well. And just like a flagpole, the longer you make it, the greater bending moment you're going to have occurring in the wellhead at the soil itself. So if we reduce, in this case, from a 3 meter stick-up to a 2 meter stick-up, which is shown in the purple, the reddy purple and the bluey purple colors respectively, we get a factor of improvement of somewhere between 40 and 50% in different load cases. And again, that's relatively typical. Something else you can do is look at the hardware that you're using. For the wellhead, you'll generally pick it for its strength rating and for its internal pressure rating. But you may want to consider whether or not it has a rigid lockdown mechanism associated with it. And by that I mean a mechanism that keeps the high pressure housing in contact with the low pressure housing at all levels of load. If you achieve that, then you're making sure that your bending moment that you're putting into the wellhead is being resisted by both the conductor string and the surface casing string at all times. There's no lift-off effect, if you like. But as well as the performance of the housing, you want to also make sure that the weld that's joining that housing to the adjacent pipe and the design of the section of the weld prep at the base of the housing is sufficient to give you suitable amounts of fatigue resistance. There's no point having a fatigue resistant wellhead if the weld attaching it to the pipe doesn't have the same level of fatigue resistance. It's a similar story for the couplings. We need to specify the fatigue requirement of the welds. But there are some specialist fatigue resistant couplings out there. I've put a couple on this slide just for examples. There are others. And then the other thing that you can do with any conductor type is you can extend the length of the extension joint below the wellhead. By doing that, you're going to push the connectors deeper into the soil and push them below the area of peak bending moment, as we've seen on the couple of fatigue life plots so far. Just to sort of reiterate that point, we have a fatigue life plot here again. Elevation from mudline down the y-axis and fatigue life in years along the x. The blue line in this case is the conductor fatigue life profile, and the red line is the surface casing fatigue life profile. And you can see that curve that's again dominated by the bending moment distribution below the soil. And then the spikes represent our first connectors. And the blue one, the conductor one, is quite deep in the soil. It's down around about 18 meters, so there's a long extension joint on this. But by doing that, we've achieved a fatigue life of around about 6 years or so at the tip of that spike. If you do a mental exercise and move it up to where that red spike is, about 11 meters, which is where a traditional 40-foot joint would end, the tip of that blue spike would be off the chart to the left. So our fatigue life would be below the 0.01 year level, which obviously wouldn't be sufficient for our operation. So this just shows you how critical that location of the connector can be in terms of your fatigue performance. Finally, on design decisions, vessel selection. Now, I've said in here that there's a recent trend to increase BOP size, but really it's been going on for quite a while now. Partly driven by a push towards deeper water, partly driven by a push towards drilling wells at higher pressure, but also that post-Macondo effect, almost a decade ago now, where additional rams started to be added to BOP stacks for well control reasons. That's good for safety, but not so good in terms of the loads that we're putting into our wellheads. As you make that stack bigger and heavier, you're going to be increasing the load on the wellhead. And then the other slightly more subtle effect is that as you increase its size, you're changing its resonance frequency and you're pushing it up to slightly higher periods. And that's going to be more likely in the region of the area of peak wave occurrences that we talked about before in those scatter diagrams. So there's a resonant effect as well as an increased load effect on the wellhead. Add those two together, you can get effects of an order of magnitude or more in some cases. Although the one that I've got on this plot here shows that we get about a 3 times improvement between rig A and rig B. On this particular case, where rig A is a 3rd generation vessel with a 3-ram stack, and rig B is a 5th generation with a bigger stack. And this is more typical. This is kind of the ones that you see where you don't get that effect exacerbated by resonance. So that's for new drill wells where you can do a lot in the design, but what about older wells where the design is essentially fixed? So you can still do something with the vessel, but what's complicating matters here is that depending on the age of the well, the inherent fatigue resistance of the equipment used in the original design may be quite low compared to modern standards because it was probably going to be drilled with a smaller stack, for instance. And the other complication is that because you're looking at this well halfway through its life, it's already undergone some drilling operations. So it's probably been drilled and completed, perhaps worked over and intervened on in the rest of the time. And so some of its fatigue capacity has already been used up. And what we need to do first is understand how much of that capacity has been used up, so we know how much we have left for our proposed planned operations. And because of those complications, simplistic assessments are unlikely to yield workable results in a lot of cases. So you might need to do some historical data dive to see what information you've got to improve the analysis. And that might be looking at things like the actual weather that they experienced during previous operations, either from recorded measurements or from hindcast modeling. Looking at wave directionality and the vessel heading, how that lined up during those old operations. Looking at operational information, things like riser tension and mud weight that were actually used during those old operations. And anything that you've been able to do in terms of calibrate the model, either through monitoring data, that I'll talk about shortly, or with looking at data from offset wells that have gone through a similar process to improve the accuracy of the soil model and improve the analysis that way. And then the last thing is going back to the OEMs for the hardware that was used for the wellhead and the connectors, etc., and seeing if they've got any refined design information for SCFs and fatigue performance as opposed to what they had when the well was originally specified. But after doing all that, there's still a significant possibility that your target fatigue safety factor of 10 may not be achieved. And in those cases, that's where you need to look at other mitigation strategies. So some of those can include seasonal restrictions, so restricting operations to just more favorable seasons. And one example of that is shown down on this plot to the bottom right of this slide. This is actually for a new drill well, but had a very high stack on it for different reasons, and so it was proving problematic fatigue-wise. But if we look at the blue line, which is completion operations, just as an example, if we start operations on the 1st of March, we're going to maximize the summer, and we can have 200 days of operations on the well before we go past our fatigue limit. If we start on the 1st of November, we can only have 50 days because we're operating through the winter season. So other things you can do, smaller diameter risers and stacks. Can you get away with using a smaller BOP stack, for instance, particularly for abandonment operations where you have got very restricted amount of fatigue capacity left? Or can you use a fixed vessel rather than a floating one if your water depth is shallow enough? But if none of that works, something else you can look at is a BOP restraint system, such as a tethering system. There's an example shown top right here. This one's got suction piles. You can use any sort of technology to anchor one end of the tether to the seabed. That can be clump weights, embedded anchors, suction piles, whatever it is. And then you have tethers between those anchors and the BOP itself, just restricting the motion of the BOP. And if you engineer that correctly, then you can get 1 or 2 orders of magnitude improvement in your fatigue damage rates by putting one of these systems in place. And then the other mitigation strategy that's available to you is the use of structural monitoring. Again, useful where required safety margins are not achieved. It's quite challenging to measure motions of the wellhead system itself directly for access reasons, and also because the wellhead doesn't actually tend to move that much itself. So what we tend to do is we put loggers on the BOP, on the subsea equipment, measure motions there, and then convert those motions into fatigue damage rates in the components that we're interested in through transfer functions that we've extracted from the analysis. That allows us to derive in-service fatigue damage rates, and if we're recording and monitoring the environmental data at the same time, then we can force the analysis model with that environmental data and extract fatigue damage rates for the same conditions and compare those to the measurements. Then we can calibrate our model and we can improve our assessment of both historical and future fatigue damage. So that leads me nicely on to the final question, which is how good are your models? And this slide just shows an example of the use of structural monitoring to answer such a question. So we have cumulative fatigue damage on the y-axis, and we have the timeline of the event along the x-axis. And then the blue line is the significant wave height trace throughout that operation. The green and the red lines are our cumulative fatigue damage lines. The red one is damage calculated from the measured motions from a structural monitoring system, and the green one is fatigue damage calculated from the analysis for that same blue environmental conditions that we actually saw during the operation. And you can see that the lines do deviate, but in terms of a ratio, they stay fairly constant between them, and that ratio is about 1.5 on fatigue damage. And that's fairly typical. With good calibration of the model, we can usually get within that factor of 1.5 to 2, which kind of equates to a factor on bending moment of between 1.1 and 1.2, so pretty close to reality. And we do that quite often on a project-by-project basis. But my final slide before I wrap up is this one that just summarizes some very recent JIP work that we've done to try and look at such calibration activities across a range of different data sets from different basins, from the North Sea and from the Gulf of Mexico, and in a range of water depths ranging from about 300 meters to about 1900 meters or so. And we had 9 participants for the first phase of this work, and we took measurements from 10 different drilling campaigns and reanalyzed them using consistent, up-to-date analysis techniques. And the results are kind of summarized in the 2 plots to the left. We have wave fatigue results on the top plot, and we have VIV fatigue results on the bottom plot. And they're shown as scatter, so each dot is the comparison of a measured fatigue event versus the analytical prediction for that same event. Any dot that's above the grey line that goes from bottom left to top right is a conservative dot, so the analysis says that we should have more fatigue damage than we actually recorded. Any dot below that line is an under-conservative dot, so we got more fatigue in real life than from the analysis model. And you can see that the majority of the dots in both cases are on the conservative side of the line, so that's pleasing. But there are some that are on the under-conservative side. And the other thing that's notable is that there's a lot more scatter in the VIV results than there is in the wave fatigue results. So if you average all of those dots, we get these kind of factors of conservatism, but obviously they don't apply in all cases, and some of these projects were more close to reality, around about that 1.5 to 2 factor, than some others. There are some outliers that are driving these numbers up. So for phase 2, which we're hoping to kick off in Q4 2020, a couple of the main objectives. First of all, to evaluate the effect of wave motions on VIV fatigue. We acknowledge that there's more scatter in the VIV results, and partly that's because we tend to analyze these things separately, whereas actually if we analyze them together, we might be able to improve our VIV prediction. And also looking in more detail at the actual probability of VIV occurrence. It's still true that the analysis says we should get VIV more often than we actually do in the field. So that's really going to be the main focus of that phase 2 work. As I said, scheduled for Q4 this year, 2020, and we're accepting new participants at the moment. So if you're interested in joining us for that, then please let us know. So that's almost it from me. The summary, just to wrap up really, I posed 5 questions at the start, and hopefully I've answered them. But just to run through them, firstly, what is fatigue? It's progressive and localized structural damage that occurs when a material is subjected to cyclic loading, and it's really that cyclic loading bit that's key for a fatigue mechanism. What does a fatigue life result really mean? Well, it's the time with the drilling riser connected before the chance of a fatigue failure is higher than the allowable probability. And for drilling and completion operations, we're told that we should be operating at probabilities of failure around about 10 to the minus 5 or so. For new drill wells, you can generally design fatigue concerns out of your projects. But for older wells where you don't have control of design, you're going to have to look at that historical data to see what's available to you to improve the accuracy of the model. You might have to assess using a reduced safety factor, or you might have to look at other mitigation measures like structural monitoring or structural reinforcement. And finally, how good are your models? With good quality design data and a calibrated model, measured fatigue can often be within a factor of 1.5 to 2 of the analytical result. And our recent JIP work has shown that can be consistently achieved across all water depths, wellhead types and soil conditions, but there are some outlying cases that will be the focus of the next phase of work. So that's it from me. Thank you very much for listening, and I think we're now going to go into the Q&A session.
Okay, thank you so much, Phil. That was great. We've actually had a few questions, so I'll get started asking those. The first question, is there actually any case history of wellheads failing from fatigue?
That's a classic question. The simple answer is yes, there have been. The most famous case is probably the Brittle failure due to VIV, which was west of Shetland back in the early 80s. I think it was 1981. It was around about 400 meters water depth or thereabouts, and we had VIV between 5 and 12 seconds with about 2-degree angular motion at the base of the riser, and that wellhead failed in about 29 days, so just under a month. But we acknowledge that there haven't been a large number of failures out there. But more commonly what tends to happen is that issues get picked up before they get to a full-on fatigue failure. So we've seen numerous examples of operators experiencing excessive wellhead movements, and we're talking angles of between 5 and 10 degrees, so much more than the 2-degree angle that we've seen with the Brittle case. And those have occurred due to either insufficient soil support for their conductor or some kind of resonance effect. And in those cases, what tends to happen is that the operations are stopped, because nobody likes the BOPs moving around that much. And because the fatigue analysis says that the damage rates are too great to continue in those scenarios. And then the well is respudded and we carry on from there. And there is some conservatism in the calculation of those damage rates, but that's deliberate for the reasons that I've kind of gone through today. Another thing that we see that's indicative of fatigue failures is the failures of lock and latch rings in the wellhead. So that thing I was talking about making sure that the high pressure and low pressure housing stay together at all times. We've actually seen some failures of those rings that have allowed separation between the high pressure and low pressure housings. And then when you turn the well on to production, you have a thermal effect that actually grows the surface casing upwards and sticks it out of the low pressure housing much more than it should be. That then leaves it unsupported laterally, and then the difficulty with that is it makes it challenging to actually land the BOP back on the well for interventions and abandonment, etc. So generally speaking, what we're doing with the conservatism and the fatigue approach is trying to avoid these things happening in the field just as much as avoiding the catastrophic failure.
Okay, next question. Should we use higher safety factor for VIV analysis considering the uncertainties in the subject?
That's a good question, and different operators have different opinions on that. Some say yes, we should, because we see cases where VIV prediction is under-predicted by factors of 20 or 30 or something. So if you want to be super safe, then yes, that is one option that's available to you to make sure that all of that scatter that I showed in the GIP plot ends up being north of the line. My personal opinion is that I think the guidance in the codes is suitable enough in most cases. But in cases where you have current profiles that are either unpredictable or cases where they're going to be so extreme, sort of single event things like spring tide currents and stuff that only happens once every so often, then yes, it might be prudent to put in a certain greater safety factor than those design codes would imply. But you need to have very good knowledge of the operation to actually apply those sensibly, and I wouldn't necessarily say that we should do it in every case.
Okay, next question, a bit of a long one. When we talk about well joint on wellhead as a hotspot area, the bending moment due to rise of load usually decreases downwards along the wellhead extension. Hence, the further join from the housing, the smaller fatigue load it will see. Does a similar reason apply in conductor housing?
Yes, so I guess the area of peak bending, it kind of tops out around about 4 or 5 meters in some cases below the soil. It can go down as low as 10 in softer soils. But the portions of the system that are just above the top of the soil see amount of bending as well. You can imagine it's the rest of the curve, right? That is the distribution around there. So the shape and the depth of that curve, that fatigue life distribution, is going to depend entirely on your soil properties, or very much on your soil properties. So that's a case-by-case answer, but generally speaking, the closer that you sort of get to the mud line, the worse situation you are, because that's the main portion of lateral restraint. So as you move further away, it's kind of opposite to that to the wellhead stick-up effect. Whereas you kind of, on one hand, you're exacerbating things if you have a higher stick-up because you're moving your BOP stack and your subsea equipment higher up. But then on the other hand, you're actually moving your wellhead components slightly further away from the area of lateral support and the area of peak bending. So in those cases, what you need to start looking at is the fatigue damage rates in the first and possibly the second connector down your conductor and your casing strings, because they're going to be moving upwards towards the area of peak bending.
Okay. Sorry. What types of inspections can be carried out to permit a use of less conservative or lower safety factor?
Right. So inspections in subsea wellhead equipment is very difficult, mostly for access reasons. In an ideal world, if you could access it, then yes, you could do your NDT, you could use ultrasonic techniques and phased array and all of that stuff to inspect the presence of defects in the materials during operation, and then that would give you an idea of where you are in between the initiation and the propagation phases, so you can recalibrate your fatigue equations that way. But really, in reality, By the time that you've put the wellhead into the soil, access for inspection and reliability of those inspections at those kind of water depths is very difficult, and not really something you can rely on. So the only thing that's within your control inspection-wise is actually at the fabrication stage, to make sure that you haven't got flaws in your welds, for example, and to make sure that you meet the fatigue requirements that your weld procedures were written to achieve. And then really for a subsea wellhead fatigue point of view, it's not really inspection that we use during service life, it's structural monitoring to measure those motions.
Okay. How would you recommend I go about selecting connectors for my conductors and casings?
Okay, I mean, an easy way to compare connectors is to look at the fatigue details, so the SCF and the SN curve that goes with it, and they'll be provided by the vendors. They're usually pretty good at that these days. However, the challenge with that is that the connectors or selection of them usually is part of a broader package. So by saying that we only can have those certain connectors, then you might be reducing the amount of available hardware for you for the rest of the subsea production system, for the pipe and the wellheads and everything else. So really the key thing to do is to do the analysis early on in the design process for the well. That will identify whether or not the connector choice and where you place them are fatigue or strength critical or not. So it tells you how much freedom that you've got in that selection. And then by doing that initial analysis quite early, it gives yourself time to react. So you can put in the limiting fatigue requirements or the limiting strength requirements into the package for the rest of the SPS equipment, and then that way you can put the responsibility on the vendors to make sure that they meet those requirements. And the analysis itself is a relatively cheap activity, so although you're doing it early and you might not have all the design data that you might need to get it really refined at that point, it'll at least give you a good indication of where things sit, and then you can always refine it later on, and there's not really much of a cost to the project about that. And then finally, the last thing is to be sensible about where you place those connectors. So look at your bending moment diagrams once you're happy with your soil information, and make sure that you plan your pipe tallies accordingly so that you don't end up with connectors placed in areas of peak bending. The same thing goes, I didn't really mention this during the presentation, but extending the extension joint is a good thing, but to do that you often have to introduce a weld at some point along its length. And that's the same story for if you're swaging down from one conductor size to another one. Make sure that you're also specifying the fatigue requirements for those welds and those swages in addition to the connectors themselves. But if you do all that right and you've go through that process early enough, then it's often the case that the vast majority of readily available connectors will work if the system response is well enough understood.
Okay, perfect. Our last question. I need to abandon a well, and the analysis shows the fatigue life was mostly used up during drilling. What can I do?
Right. So I guess the first thing really is to critically examine the analysis work that's telling you that in the first place. Use fresh eyes if possible to send it out for verification. Look at things like the weather data. How accurate was that? Are we using actual recorded data, or are we using hindcast data for the months and years of the historical operations? And how good is the soil model? Is there any way that we can calibrate that? Is there any records from drilling or from offset wells that will help us understand a bit more about the soil characteristics? Then look, before we go back to the analysis, look more at the operations that you need to do and examine what actually needs to be performed with the rig and what the rig requirements are. So what kind of stack size do you need? It's a good time to actually ask that question, because a few years ago in the last downturn, 2015, 2017-ish, we found that a lot of operators were very tempted to go for super capacity rigs, ultra deep water rigs that were available on bargain basement rates to do operations in pretty shallow water and pretty old well stock. And the challenge is those rigs were generally never designed for doing that kind of work in shallow water. So you actually get into significant resonance issues, and just stack size itself can lead to excessive bending moments on the wellhead. So think about that critically, and rather than going for a super capacity rig, go for one that actually suits the operation that you're planning to do. The next bit, obviously, it's fairly straightforward, but do it in a sensible time of year. So do it when the conditions are going to be benign. And if that still doesn't get you to where you need to be, then you need to start looking at risk assessing that lower factor of safety. And for abandonment, which I think the question was about, in particular, by definition, they're usually occurring on depleted wells, and they're at the end of well life. And really what the thing that you're going to be doing after you've abandoned the well is cutting the wellhead and retrieving it. So when you get a fatigue failure in those cases, is perhaps not as much of a risk consequence as it would be for a new drill well, for example. Structural monitoring is another way you can put in a real-time system to look at developing condition, but that can be difficult, and you need to examine carefully what the order of events, the causation of fatigue is, the sequence of fatigue failure after the first one onto the second, etc., to make sure that you know what you're looking for. But then really the catch-all on the end of all that is that if none of that works, the tethering option is a good one because you're almost guaranteeing 1 or 2 orders of magnitude improvement. And although it's not the cheapest solution, it's also not prohibitively expensive, and the cost can really average out quite reasonably if you use a single tethering system for a number of wells.
Okay, great. Well, thank you, Phil, so much for all the information on the topic. That's all the time we have for today. And as I mentioned earlier, if we didn't get to your question, or if you'd like to continue the discussion, please contact Phil directly using the details provided here. Thank you to our audience for your time and participation, and we hope you all found this useful and will join us for more webinars in this series. They're going to be happening every 2 weeks during our time at home. Check out the 2H website for more details and to sign up. And again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you enjoy the rest of your day.